I think a lot about physics as being a science, an observational science. The most critical thing is that physics is a description of the universe. We observe the universe through scientific measurement, and we look for patterns in the relationship between the measurements we make, and we call these physical laws. But physics is a description of the universe, and if you take a more elementary physics course with me, you know that one of the first things that I start off with is saying, this is the universe and you are here. The location of an object or an event in the universe that we call position. Position is the most fundamental measurement that you can make. It's the measurement of location in the universe. I could go through a whole thing here. I don't have time to talk specifically about coordinate systems, but it's a critical idea. The measurement of the location of a thing in space is meaningless without a choice of coordinate system. I have to emphasize that because young students of physics often miss out on the subtlety of this point. Physics or engineering or any of these derivative fields cannot be done without first choosing the coordinate system. Very often we do it without even realizing that we've done it. You have to choose a location that is called zero and choose a unit of measure from which you mete out tick marks to identify the location of things. There is a wonderful thing going on behind the scenes on this, and sometimes when I'm doing an AP physics lecture, I'll be talking about something very simple like location, position, and I'll say something very, very deep, but it's hard to grasp how deep it is. I want you to tune in on this. Measurements of position are not, very likely, are not the way you think they are. You have to be very careful about what's actually happening when I make measurements of position. Because what I do is I choose a coordinate system and I look at a thing. Think about it in a very simple mechanical way, something obvious. Like there's a ball, there's always a ball somewhere rolling to and fro, and there it is. And I look where it is and I look in relation to the tick marks. Well, a thing that those who have taken the honors physics course realize is that the tick mark isn't lined up exactly with the location of the thing, and so there is uncertainty in measurement. That's true. There's no such thing as the exact location of an object. It's the measurement that exists, not the object itself. That's fun, deep stuff. Yesterday I was talking to an academic physics class. I just wander into physics classes. I sometimes wander into biology classes. I don't know if you've ever seen me do that. Maybe when you were a youngster, I just came charging into your biology class and started mouthing off about science and whatnot, maybe. But I wandered into a academic physics class yesterday, and they were measuring the tables. Some of you remember doing that, measuring the table and getting the uncertainty associated with that measurement. And so they were talking about the table and the length of the table. And I was asked what my opinion was. The fact of the matter, I don't have opinion. It's the way things actually are. But I pointed out, let me tell you that the length of the table, which is necessary for me to determine the area of the table, the length of the table has a problem of definition. This is what I mean. We say, what is the length of the table? And you look at it and quite simply you go, well, it's from there to there. As a practical matter of conversation, the length of the table is easily agreed upon by you and I. It's from here to here. But when I go to measure it, I'm going to use a meter stick that has tick marks. Some of you are very aware that I get to this end of the table and I look and the tick marks don't exactly line up, so I can't be sure. And that is the uncertainty in my measurement. I have a set of rules that have been devised that are very fair in assessing the uncertainty in the measurement of position. But no, you say, here's the thing. You can actually know the length of the table. You just have to be more careful about it. You have to do it in a better way. Well, let's do it in the best way we can possibly imagine. Let's transcend using a caliper or some big apparatus. Let's transcend using lasers. Let's imagine that we have God-like ability to make a measurement. But the fact of the matter is that the table is made of molecules. And when I get to the very end of the table, not only this end of the table where I complete my measurement, but the beginning of the measurement over there, the molecules are sort of ambiguous. When you think of molecules and atoms, you might think of marbles all connected together. It's not that way at all. But for the purpose of this discussion, let's just let that be okay, that it's just a big ball of marbles connected together with springs, but it vibrates. And the vibrations of molecules on average is what we define as the temperature. But the fact of the matter is the molecules wiggle over here and they wiggle over there, so the table gets a bit longer, it gets a bit shorter. So in a fundamental physical way that is immutable, as far as we know, according to the laws of physics, impossible to get past. There's no such thing as the length of the table has a problem of definition, because the length of the table is the difference between the position of one end of the table and the position of the other end of the table, and those positions are fundamentally uncertain. But for us it's worse, Because when I make a measurement of position, I make a measurement of position in an instant in time. And there's a thing that our human brains do that is a really bad idea. Here is my marker, and now I can speak about its position. And I can say, there is the marker. And I can go over here lecturing and look out the window very thoughtfully. Makes me seem intense. And say, and yes, that marker sits there. How the hell do I know? I'm looking out the window. Is the marker still there? And your little primate brain goes, of course it is. Object permanence, like with babies, right? Peekaboo. Oh, and the baby. No, and the reason why babies are delighted by this, you learn in psychology, the reason why babies are delighted by that is when you put your hands over your face, they think you've disappeared. Because a baby's mind has not yet figured out object permanence, which makes the baby smarter than us. Because I'm not looking at that marker right now. I don't know that it's actually there. I could gather indirect evidence of the marker. I could take out a mirror, right? Or I could ask you sort of indirectly or whatever. But those are just indirect forms of measurement. And the measurements are fundamentally uncertain. And all of a sudden, the existence of the marker becomes crazy, crazy uncertain and a deep thing to think about. Now, you might be sitting there thinking, yeah, but none of this matters because the marker is there. Well, that's true. That I can create an entire physics, the physics that we learn in this first semester, I can create an entire physics based on the notion that that marker has a definite position that I can define. And that if I change the position of the marker, well, that's okay, because now I have an initial position, a final position, which I can subtract and call displacement. And I can define all these things, but I have to be careful about the definitions, because the fun thing, and I can't help myself, electrons don't behave that way. Electrons don't do that. And you say to yourself, wait, oh, I get it. I could say, because the electrons are so tiny and they're so difficult it's difficult to keep track of. The markers are easy. No, it's not. That's not the issue. Electrons have fundamentally different behaviors. So this physics that you're going to learn in the first semester is a beautiful, wonderful thing for your imagination. This physics that you're going to learn in this first semester doesn't apply to atoms. Oh, I get it. It's really hard to apply to atoms. No, it does not. It is incorrect fundamentally. Isn't that fun? So even in the simplest thing of physics, that is the position of objects in our universe, even in that very, very fundamental aspect of our physics, there's wonderful subtlety to it that we should appreciate as we go forward. And I'm going to sort of weave that into what I'm saying. So I start off with, I regret here, sometimes I write things on the board and I think to myself that I really need to write that position. And I'll say the definition out loud without writing it. I don't want you looking at my back while I write long sentences on the board. But position, according to me, is my definition. Your textbook probably says. The definition of position is the location of an object or event in a given coordinate system. Oh, that's very, very dry. So the position, which I typically give the symbol X because we often do things in one dimension. And one dimension implies to me from a tradition of mathematics to be the x-axis. And I go along with that and I call the position X. A thing that you will see me do throughout all of our physics is I will write these brackets here. This is another sort of Shidleyism, an unconventional thing that I do, but it turns out a useful one. I'll write these brackets all through the course from the beginning to end, right next to a quantity. What those brackets mean is the units of the quantity. I could go on and on about dimensional analysis of units and how useful it is to you. You recall yesterday I showed you a potential AP physics test. And in one of those problems, there was a very complicated looking equation that was in no way obvious. There are some results of physics that are completely obvious. For example, the distance a thing travels is its speed multiplied by its time. That is grotesquely odd. No, it's beautifully obvious. It's grotesquely obvious. It's beautifully obvious. Because if the speed of a thing is the number of meters per second, and I multiply by the number of seconds, then I get the number of meters. It's completely obvious. But when we do a more sophisticated physics, like we choose to do, that physics is going to end up in results that are in no way obvious. So I had shown you the equation, sort of quite arbitrarily, for a distance a projectile travels when it flies up an incline, and the distance up the incline that it lands. A very complicated equation with sines and cosines in it and so forth and some squares. You might derive that answer for yourself and look at it and say, after much labor of algebra and going through it and making some assumptions and things along the way, am I doing the right thing? I'm not sure. And then you do it and you complete it and there it is. Is that right? Is that the right answer? Is that the correct answer? And it's actually going to happen to you during this course. And heaven forbid it happens to you on the exam itself when you're under pressure. You get an answer and go, I don't know if it's right. The easiest way to know whether your algebraic derived answer is correct or not is to check the units of the equation. In it, there are quantities like position, for example, of units of meters, and velocities of meters per second, and accelerations of meters per second squared, and Lord knows what else, magnetic fields, electric fields, forces, mass, and so forth, and inertia in kilograms. And all of those units, and put them together and cancel them out and figure out ultimately what those units cook down to. And if they're the quantity you're looking for, then you potentially have the right answer. It could be you're still wrong and it just happens to have the right units. That can happen. It's far less likely. So sometimes students will come to me with things and say, Shiley, I don't know if this is right or not. And I'll look at it and go, it's wrong. Yeah, but how? Why? I have no idea. Well, how do you know it's wrong? Because I look at the units and it's not right. It doesn't work out to meters per second. You're saying the velocity equals this, but the units don't turn out to be meters per second. So knowing the units of the quantities that I'm working with is of critical importance. So I write them in brackets to say, look, be careful here and make sure we're aware of how we're measuring things. So I'm going to measure position in meters in physics traditionally, although in your homework you're going to encounter other systems. But meters is the standard. But the location of objects in the universe is not the interesting thing about the universe, because if I could define a coordinate system and then locate every object in the universe, well, I'm done. Happily, the universe is more interesting than that, and things change their positions, which is really the issue. We live in a universe of change, a universe that evolves. And so positions can change. And so I define the displacement delta x, which is the change in position. A definition, a physics definition. Did you ever stop to think? You probably didn't. Could you do it a different way? Funny thing is, Albert Einstein stopped to think, could you do it a different way? And just for fun, I guess, Einstein's idea of fun, he, instead of defining displacement, as we all do, as the final position minus the initial position, he decided to do something, I can't remember off the top of my head exactly what it is, but some relationship among the squares or something. Oh, you can't do that. Yes, you can, because it's by definition. You're the one making it up. It only matters then, is it useful or not? So can I make a different definition for displacement and derive from that a perfectly legitimate physics? Yes. It turns out that physics is really hard to do because it gets complicated. The more mathematically complicated I make displacement, everything else down the line gets more and more complicated. So it turns out to be a really bad idea, but it can be done. So by definition, this is displacement. And because the final position and the initial position are in meters, this works out to be meters, and everything's great because now I can look at the universe and locate the position of every object in the universe. But, and this is the important thing, like the subtle thing about this aspect of physics. I turn my back on the universe, and while I've got my back turned, everything shuffles around. And when I turn back again, everything's in a different position. Now, again, the primate mind says, things moved through a continuum of positions, right? So I put the marker here, right? There's the marker. Close your eye. You open your eyes again. Open your eyes again. Huh? What happened? I moved the marker, didn't I? When I moved the marker, did it exist at every position in between? No. You have no way of. You completed the idea. And there are some folks in here like, yeah, but he had his eyes closed. Everybody else was watching. It moved through a continuum of positions. Did it? How do you know? Because I was watching it. Oh, you mean the light went into your eye, stimulated your rods and cones, went into the cortex eye of your brain? That's not even a word. Created an image? You know that your brain has a frame rate, right? You don't see continuous. Your vision is not your brain creates one image after another. What was the marker doing in between? Right. But my question is, did it exist in between? No measurement was. Continuous motion is in. Can you say with absolute certainty that the marker did not start here, go partway across, appear on the other side of the universe, appear back here again, move to that position? Can you say with certainty? No. And it's not even the limitations of your ability to measure. So far as we can tell, it is physically impossible for you to know, because all you know is the initial and final position. You do not know what happened in between. Now that's not going to turn out to be an extraordinarily relevant idea to this physics, but when we get to the spring and we finish our exam, I'm going to start talking about the fancy physics that's become very relevant, because it matters. If I see an electron over here and I see an electron over here, I cannot assume that it went from. That notion of continuous positions from one location to the next is what we call in mechanics a trajectory. In our physics, that is classical mechanics that we study here, trajectories exist. In reality, and by reality I mean the observable universe to the extent that mankind has understood physical laws associated with that universe, no. There's no such thing as trajectory. There's no such thing as a path of continuous points. Just like there's no such thing as the length of the table. So relax, the table's holding your stuff up, right? As a practical matter. Where's my marker? As a practical matter. So then I've got it because I figured out the displacements of everything in the universe. But it's trickier than that, you see, because one object starts here, another starts, and I calculate its displacement. But in the same interval of time, other objects in the universe displace themselves with greater displacements, or lesser displacement. That is, the rate at which objects displace is different, and so we define a quantity that we're all already familiar with because of our studies prior to this. A quantity known as the average velocity that is defined as the displacement divided by the time in which the displacement takes place. This notation that I've used, delta x is the displacement, because the delta symbol means change. So it is the change in position divided by the change in time, the time at which that change in position takes place. So I have an initial position, a final position, and I know the time interval between those two position measurements. I simply divide, and I get a quantity known as the average velocity. Now, I probably should mention speed here. If it were a more fundamental physics class, not more fundamental, actually, if it were a more general physics, that's what I should. Then I would talk about speed, but the fact of the matter is speed is a less useful quantity because it's not a vector quantity. I have some stuff to say about vectors today, but for the moment, speed is a less useful physics quantity, so I can actually just talk about the velocity constantly and not worry about speed. So here's the velocity. So what's happening is an important point that I want to make, is that the velocity here is defined only on average. We're going to make a distinction here. If I make a graph of the position as a function of time, in order to describe a velocity, I naturally must make two position measurements and two time measurements. I can always, of course, choose the initial time to be 0. Say it starts at 0, and then sometime later we do that as a matter of practice. But I need two position measurements, at least two position measurements, in order to define what velocity is. So let's say that I have a trajectory. Charlie, you just said trajectories weren't a real thing. Yeah, do you see that? I'm breaking the own rule in order to describe what's happening. So the object has a path, takes a trajectory through space-time that we see here. That's what it does. But the reality of my measurement is that I measure an initial position over here, and I call this x1. And I measure a final position over here, and I call this position x2. And those two positions allow me to calculate a displacement delta x from the initial position to the final position. But do you see that that does not really describe the actual behavior? Because it implies that I'm going from here, try to do that on your own graph, draw a line between 2 points that you already drew. It implies that I'm going a straight line. No, it's curved. But you see, I didn't see that. I only made two position measurements. I don't know what happened in between. All I know is that there was a certain change in position, delta x, that occurred in a certain change in time, delta t, and that is all that I know. And so my description is incomplete. My description is only on average. My description is a little imperfect. And you can see the problem. I think we all realize here that what I define as the velocity, delta x divided by t, is the slope of this line that I've drawn between my 2 points. Why did I label that? Do you see what my labels are bad here? I'm just, talking and doing stuff at the same time. I should have called this is the time axis, of course, so this is label T1, and this is label T2, pardon me. And this is label X1, obviously, that's the position X1, and this is the position X2. I'm sorry, but that's the way it goes sometimes. That's why you have to pay careful attention. It'll really screw your notes up if you see me make a mistake. So on the vertical axis here, I have the positions, and on the horizontal axis, I have the times. Well, this velocity that I've defined, delta x divided by delta t, is the slope of that. Well, you see how bad it is. Because at time t1, I can look, because I have godlike powers here, because I know the trajectory, which I can't actually know, but for the purpose of my argument. It's very steep here. The slope is very steep slope. And since the slope of the position time graph is the velocity is very high. But later on up here, I get the slope is very shallow, in fact. So the velocity is very low. So I do this calculation, delta x over delta t, and I claim knowledge of the velocity. But the fact of the matter is, during the time interval, delta t, the velocity changes continuously from the beginning to the end. So it's not a very good description, is it? There's only one thing that I can do about it. There's only one way that I can change it to make it better. And that is to shorten the interval delta t. Don't let it go on for so long. Because if you turn your back on the universe for a long period of time, it's going to get up to some nonsense. And then your description of the universe is going to be more imperfect because you turn your back for too long. So you've got to shorten the time. Shorten the time interval. And I'm not going to mess around with it. I'll shorten the time interval. So I'll shorten the time interval very small. Because anything worth doing is worth overdoing. That's what my grandfather said. So I'll make the time interval very, very small. And when I make the time interval very, very small, you see here on my time axis, if I sort of follow that down, the time interval is very, very small indeed. I have this large time interval between T1 and T2, and I call that delta T. So this time interval is much, much smaller. I can't call it delta T, I have to call it something else. Oh, I know. I'll call it dt. D is in delta. You see, I just replaced the delta with d. So delta T is a time interval. And I'm just asking us to agree that if I make a really small time interval, I change the delta out for a d to say it's really small. Well, Charlie, how small is it? Pretty damn small. You know, if I make delta t much smaller, call it dt, well, that means necessarily that the interval on the x-axis is going to get smaller as well, because I have this large interval, which is delta x, and now I have this little one, which, let's keep with the naming convention. I'll call this dx. I don't change my definition of velocity at all. So my velocity is now defined as dx over dt. Which, that's the same velocity. Yes, but it's a little bit better. It's improved because I made delta t so small that when I draw the line through it, that is the slope doesn't change much on the interval. It's a fact, think about this kind of deep, it's a fact of every real function in existence that if you look closely at it, it becomes a straight line. Just zoom in, zoom in, zoom in, zoom in, zoom in. Draw a circle on your computer and then just zoom, 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 zoom. It becomes a straight line. But let me go back to this graph here. So now what I've done by making the time interval very, very short is that I know what the slope is right there because it doesn't change much between the initial and final. And if you zoom in enough, it's guaranteed. You make the argument, you say, well, Charlie, I don't think you zoomed in enough. I'm not convinced. Well, I'll zoom in more. But I can zoom in. I have the option to zoom in infinitely. And if I zoom in infinitely, the interval dt becomes infinitesimal, doesn't it? Now, we can't conceive of, what does infinitesimal actually mean? Imagine infinitesimal in your mind. You cannot do. But the argument exists that I can make the interval arbitrarily small, and so therefore infinitesimally. When I do, that means that at that position, I know the velocity at that instant in time. I know the instantaneous velocity. So this is what we talk about. We talk about quantities on average. And by the way, velocity is not the only quantity that in our physics will be defined on average. So this idea about the difference between speed, or average velocity, and velocity in the instant, it's going to come up anytime we define rates in physics. It's going to be a notion of what we do. So this becomes the instantaneous velocity. As I make the delta t, as I make the time interval smaller and smaller and smaller, the delta x, or the dx, gets smaller and smaller and smaller. There must be some relationship between dx and dt. Of course there is. I'm going to write something utterly unsurprising, that dx is equal to v times dt. I'm not wasting your time with this. Because embracing this idea will help you solve physics problems through the entire course. It's critical. And I know, I'm about to say something utterly obvious, but I need you to embrace it, internalize it, believe in it deeply. If I'm moving with a velocity v, and I let a tiny little bit of time pass, dt, I will travel a tiny little distance, dx. My point is this. This is exactly the same equation as the distance that you travel. I'm alarmed about using d here, but I think you can handle it. D is equal to v times t. It's the same equation. The same simple, obvious, utterly transparent equation that we'll learn in the lowest level physics class that there is. Those two are equal to each other. The only difference in the statement is if I make a really tiny step in position takes a really tiny bit. That's the simple relationship that's going on there. There's no reason to be afraid of it. It's completely obvious. And if you can take a deep breath and transcend that, the peculiarity of the notation, I've never seen it before, it's strange. If you can transcend that, then you are much further along your way of understanding calculus. Because believe it or not, that's all calculus is. And I'm going to show you that in a rather spectacular way going forward. I've got it. I figured out the positions of everything, but I turn my back and the positions all change, and they don't all change by the same amount in the same interval of time. So I define the velocity on average. I realize that that's not giving me the full picture, so I think about it a little bit. If I shrink the interval, I can find what the velocity is at any instant in time, and so my velocity in meters per second is well defined. The trouble is that's not the end of our description of the universe, because I find that if I look at one interval of time and measure the velocity of everything in the universe and imagine myself done with my labors for the day, that if I turn my back on the universe again and then come back, that the velocities of individual objects in the universe may have changed. That is, the velocity can change. So I define the acceleration of an object. The acceleration is equal to the change in the velocity divided by the time in which that velocity changes. Now, the next thing for me to do, I suppose, is to draw a graph of this and whatnot and make the same argument that I just made. The fact of the matter is that quantity that I define as the acceleration, by the way, with units that are meters per second for the velocity divided by seconds, a set of units that we very lovingly call meters per second squared, the units of acceleration. That quantity is defined on average similarly. I do not know what the acceleration is at every instant in time. Do not know. But by an identical argument, an argument so identical that it's not worth making again, I can write that the acceleration is equal to dv dt. A tiny little infinitesimal change in velocity takes place in an infinitesimal change in time. And by virtue of the same algebra, I can solve this around and say dv is equal to a times dt, which says that if I have an acceleration a at any instant in time, in an infinitesimal interval of time, the velocity will change by an infinitesimal amount. And that is that change in velocity is proportional to the acceleration. Do you see that this is identically that obvious statement of what we call kinematics? That's it. May look a little bit familiar if I realize that delta v, of course, is going to be the final velocity minus the initial velocity. And so delta v is v minus v naught. Add the v naught over to the other side of the equation. This is v is equal to v naught plus a times t. An equation useful for solving kinematics problems that is a direct consequence of the definition of acceleration. Now, very often when you take an introductory physics class, we stop here. Actually, we stop a little bit before this and say, let's let the acceleration always be constant. Let's let the acceleration not change. Because when the acceleration changes, the math gets complicated. Well, this is AP physics. So whereas for those of us who had taken honors physics, we force the acceleration to be constant, in this course, hooray, we will allow the acceleration to be a function of time. Acceleration can change. And then the physics of things become quite interesting and can solve problems that we were never able to solve before, using some slightly more sophisticated techniques. You might imagine, I can go on with this forever and ever. Just keep defining. In fact, we do. Just a little fun. If you define the rate of change of the acceleration, that is dA dt, has a name. It's called the jerk. And if you define the derivative of the jerk, or sorry, pardon me, I didn't mean to say that. If you define d jerk dt, it's called the snap. But it turns out that those aren't of great practical use. That is, the more we take derivatives, we can't solve more and more interesting problems. We really only have to go so far before we run out of practical value to the physics that we do. So that's position, velocity, and acceleration, which was the first 3 bullet points on my list of things, so which is okay with me. I have plenty to talk about.